Dear students, I welcome you to this second lecture on electric machines. In our last lecture, we discussed the basic operating principles of an electric generator and motor. We have seen that for an electric machine, we require a magnetic field and a set of conductors. To provide support for the conductors and to provide a confined path of low reluctance for the flux, magnetic structures are provided for the stator and the rotor. So we have seen the function of the magnetic structures is to provide support for the conductors and to provide a confined path of low reluctance for the flux. What is done? Magnetic structures of iron are provided for the stator and rotor. The magnetic structure of the stator is called as stator core, and that of the rotor is called as rotor core. These are two cylindrical structures. The rotor is housed within the stator core. The two cores are separated by a small gap in order to allow free movement of the rotor. So you have the rotor core within the stator core. Then, in order to accommodate the conductors, slots are cut on the surfaces of the stator and rotor. We cut slots on the surface of the stator as well as on the rotor to provide space for accommodating the conductors. So these are the stator slots. We can put conductors in the stator slots. These conductors are then connected in a certain fashion to form what is known as the stator winding. Similarly, to accommodate conductors on the rotor, slots are created on the surface of the rotor. then the conductors in these slots are also connected together to form the rotor winding. When these windings are made to carry current, they establish a magnetic field. And in order to understand the magnetic field produced by such windings, we'll begin with a single coil on the stator of a machine and try to see the nature of the field produced by the single coil. So let's discuss the magnetic field produced by a single coil on the stator. So here we'll consider a simple structure So, in order to provide a single coil on the stator, we create a single slot pair, and in this single slot pair we put a single coil. This is basically a cross section of the machine. As far as this coil is concerned, it actually will be formed by a number of turns, which can be shown schematically here. You can have as many turns as required. This is how the coil will be formed, and in this coil you will have many turns, and in each turn there are two conductors in fact, and the conductors on one side will form what is known as a coil side. This is one coil side and this is another coil side. And suppose the two coil sides of this coil are labeled as A and A prime. Let this coil be supplied with a current I, and let N be the number of turns in the coil. So by connecting this to an external circuit, we'll circulate a current in the coil, and that is current I, is the current carried by the coil. And as you can see, the current carried by the coil is basically the current carried by each turn of the coil. And suppose the direction of current is such that the current on the front side, it enters the coil side A, it is flowing into the plane of the board, and on the other side, therefore, the current will be leaving. So if you have a look at this to understand this, on this side we are supplying the current I, and on this current finally the current will be leaving. Here therefore this is the coil side, say A, and this will be the coil side A prime. In these, the direction of current will be upwards. Seen from this side, the current will be entering into the plane. So we are basically looking from this side. So the current is entering, and on this side the current is leaving the coil. Now the flow of current in the coil will establish a flux. Each coil side has many turns, many conductors through which a current I is flowing, and therefore they will give rise to, the flow of currents will give rise to flux lines. And if we apply corkscrew rule for a current carrying conductor, the magnetic flux is in the form of circular paths, and the direction is given by corkscrew rule. If we apply it here, the current is entering. In order to push a screw inwards, the screw has to be rotated clockwise. So therefore this coil side will give rise to flux lines which are clockwise, and similarly this coil side will give rise to flux lines which are directed anti-clockwise. I'll draw, for the sake of simplicity, I'll draw a couple of representative flux lines on each side. The direction of flux will be here clockwise, so it will be like this, and in this anti-clockwise. Now if we have a look from the air gap, if we are in the air gap, we see that on the left half of the stator, the flux is coming out of the stator and it is entering the rotor. And on the right half of this machine, the flux is coming out of the rotor and it is entering the stator. Now since the flux is created because of the winding on the stator, we see that effectively a north pole is created on the left half of the stator and a south pole is created on the right half of the stator, seen from the air gap. Now we see that each flux line, so first observation that we see is that a north pole is established on the of the stator and a south pole is established on the right half. Second thing that we see is, if we consider a flux line, it encloses n number of conductors and each conductor carries a current I, and therefore the MMF is equal to Ni. Each flux line is therefore associated with an MMF equal to Ni. The third thing that we see is, if we consider a flux line, most of the flux path is confined in iron, and iron has a very low reluctance compared to that of air, and therefore we see that the reluctance of iron being negligible, the reluctance offered to each flux line is that of the air gap crossings, and each flux line crosses the air gap twice. On one side, when flux line passes from the stator to rotor, and on the other side when the flux line crosses from the rotor to the stator. So the next observation is that each flux line crosses the air gap twice, and the reluctance offered to the flux lines is predominantly due to the air gap. The reluctance offered to the flux is due to the air gap. So therefore, since each flux line is associated with an MMF Ni, half of the MMF will be used to create the flux in one part of the air gap, and half of the MMF will be used to reduce the flux in the other part of the air gap. So therefore, since each flux line crosses the air gap twice, half of the MMF will be used to create flux at each air gap crossing, and the half of the MMF will be therefore Ni by 2 on this side and Ni by 2 on the other side. So we see that on the left part of the air gap, the MMF that will be acting on this air gap will be equal to Ni by 2, and on the other side there will be an MMF of Ni by 2. And if we therefore plot the variation of MMF as a function of the space angle being measured with respect to an axis passing through the centers of these two poles, which is known as the magnetic axis of the stator, if we measure the angle theta with respect to the stator magnetic axis, we can plot the variation of the MMF in the air gap as a function of theta. It's angle 0 here. On one side minus pi by 2, theta pi by 2, pi, 3 pi by 2, 2 pi, and so on. Now we see from on this side there is an MMF of Ni by 2, on the other side there is again an MMF of Ni by 2. But we see that since on this side the MMF is, we have a north pole, the MMF is used to create a flux which passes from stator to rotor, but on the other side the MMF is used to produce a flux that passes from rotor to stator, and therefore we can associate a different direction to the MMFs on the two sides, different sign. And if we treat the we can establish a convention ourselves. If we treat the MMF that is used to create flux from stator to rotor, let's treat this as negative, and the MMF on the other side, where the MMF is used to create the flux from rotor to stator, it will be taken as positive. Therefore, if we start from minus pi by 2 to pi by 2, the MMF will be Ni by 2, but according to this convention, it will be taken as positive. From minus pi by 2 to pi by 2, there will be an MMF equal to Ni by 2. Then, between pi by 2 to 3 pi by 2, which is again equal to minus pi by 2, the MMF will be minus Ni by 2. Minus Ni by 2. And therefore, the MMF will vary like this. And if you go again and again, you can go on increasing the angle. Therefore, this waveform can be plotted repeatedly. We get a periodic waveform, this shape. So this shows the variation of MMF with respect to the space angle theta in the air gap. Variation of MMF with respect to angle theta. Now, it is this MMF basically which produces the flux in the air gap. Now, as far as the flux density in the air gap is concerned, we know that the flux is given by, in a magnetic circuit, the flux is equal to MMF by reluctance. And here, for this discussion, we have considered a cylindrical rotor, and the air gap is uniform, Therefore, the reluctance offered by the air gap will be constant. And this being constant, therefore, the variation of flux density in the air gap will be will follow a pattern which will be similar to the variation of the MMF in the air gap. Therefore, if we plot the flux density versus theta, V versus theta, it will be similar in shape to this. Pi by 2, 2 pi, and so on. This shows the variation of B, and B will also have, corresponding to an MMF of Ni by 2, B will also have a specific value. Suppose we call it as B max. On the other side, then it will be minus B max. So the flux density wave in the air gap is a square wave. It's a square wave pattern. Now, we know that since this is a periodic waveform, we know that a periodic waveform, any periodic waveform can be considered to be made up of a large number of sinusoidal waveforms. The first waveform has the same period and same frequency as that of the original periodic waveform, that is known as the fundamental component. In addition to this, there are many number of sinusoidals present in the periodic waveform, which have a period which is a submultiple of this, or in other words, which have frequency which are multiples of the frequency of the fundamental. Those are known as harmonics. Therefore, this waveform can also be considered to be made up of a sinusoidal, which is the fundamental, and a large number of harmonic components. So let's plot the fundamental here. If we neglect the harmonics, the fundamental will be something like this. This component is known as the fundamental component of the B wave. So in addition to this fundamental component, there are a large number of, large number of harmonics present in the B wave. Because to create this square wave, you have to superimpose so many sinusoids on this fundamental, such that the superimposition of all those sine waves will result in the square wave pattern. So this is the nature of the field produced by a single coil on the stator of a machine. So we have seen that by providing a single coil in a single slot pair, there are two poles created on the stator. So we have a single slot pair, one slot pair, per pair. This is the minimum number of slots required. We require one slot pair to create one pole pair. Now let's see how four poles can be created on the stator. Therefore, we can easily see that to create two pole pairs, we'll at least require two slot pairs. Four-pole machine. So again, we have considered a cylindrical rotor which is enclosed in an annular stator. Now we therefore have to create four slots on the stator periphery, stator surface. And now in these two slot pairs we can provide two coils. One coil A1 prime is housed in this slot pair, and another coil A2 and A2 prime is in another slot pair. Now these coils can either be connected in series or in parallels, so that they together carry a current, and once they are connected to an external circuit, suppose the coils are connected such that the current enters this coil side, you have a cross here, and therefore the current will be coming out at coil side A prime. Similarly, the current will be entering the coil side A2 and current will be leaving the coil side A2 prime. For this distribution of current, again, if we apply the corkscrew rule, we'll see that each coil side will establish a flux. And we see that this coil side will establish a flux in the clockwise direction, and this currents in this coil side will establish a flux in the anti-clockwise. Here again clockwise, and here again anti-clockwise. Let's draw a few representative flux lines. The flux here will be clockwise, this side anti-clockwise, again clockwise, and then again anti-clockwise. Now if you have a look at, if we are in the air gap and we have a look at the stator, we see from this coil side to this coil side, looking at the stator, the flux is coming out of the stator and it is entering the rotor, and therefore effectively a north pole will be established from coil side A2 prime to coil side A1. And if you go beyond A1 to A1 prime, we see the flux is coming out of the rotor and it is entering the stator. Therefore, effectively, a south pole is created on the stator over this distance. And then again, therefore, using the same logic, we see that a north pole will be established from this coil side to this coil side, and a south pole will be created in this portion of the air gap. So therefore, effectively, 4 poles are created in the air gap. So this is how we can create 4 poles on the stator, and to provide therefore 4 poles or 2 pole pairs, we require 2 slot pairs. We have used 2 slot pairs to create 2 pole pairs. Similarly, if we have to produce 6 poles, that is 3 pole pairs, we will be requiring 6 slots and so on and so forth. Now, there is an important relation between the angle measured over the air gap and the number of poles. We see, if we consider a magnetic field where you have only 2 poles in the air gap, as we had discussed previously, and if we consider a conductor on the rotor, and if the rotor is, for example, rotating, we again consider it quickly. We had 2 poles, north pole on the left side and south pole on the right side. If we consider, for example, a conductor on the rotor, and if the rotor is rotating, if it starts over this, while it is rotating, from this point to this point, it will be under the influence of a north pole. The EMF induced in this conductor will be having one direction, and as the conductor moves from this point to this point, the EMF will have another direction, because it sees a north pole over this and it sees a south pole over this portion. So, one complete revolution of the conductor will result in one cycle of variation of the EMF. So, the EMF will be in one direction here, and in the other portion EMF will have opposite direction. Therefore, one revolution of the conductor will correspond to one cycle of variation of induced EMF. But if we consider a 4-pole machine now, if we have 4 poles, say we have a north pole, south pole, and south pole, and if we consider again a conductor on the rotor, and if the rotor is rotating, we see that as the rotor rotates from this point to this point, you will see a north pole, then a south pole, then again north pole, and again south pole. And we see that the direction of induced EMF, it will change twice. It will complete, the EMF induced in the conductor will complete 2 cycles of variation of EMF, because it sees 2 north poles and 2 south poles over one revolution. And therefore, electrically, although mechanically the conductor here has moved by 2 pi, and here also it has moved by 2 pi, but effectively electrically seen here, the conductor has moved by 4 pi, because it has completed 2 cycles of variation. It is as if it has completed 2 revolutions in this machine. So therefore, we have an important relationship that you must have studied in your previous semester also. we call this angle which is measured in electrical engineering, this is known as electrical angle. We denote it by theta E. It is for a two-pole machine. For a two-pole machine, the electrical angle is same as the mechanical angle, the actual angle that we measure. Now, in a four-pole machine, what we see is electrically the angle is twice the mechanical angle. Although mechanically the conductor has moved by 2 pi only, but electrically it has seen a variation of 4 pi. If we have a 6-pole machine, similarly, we'll see that in that case, for a 6-pole machine, what will be the relation? Theta E will be equal to 3 times theta M, and therefore we can generalize this, that the electrical angle is equal to P by 2 times theta M, the mechanical angle. So before we further discuss the flux created by other windings, we'll define some basic terms here which are related to winding machines. One is known as coil span or coil pitch. Before this, we'll define pole pitch. So we have seen in a machine alternate north and south poles are created over the periphery. The distance between the centers of two successive poles, the distance between the centers of two adjacent poles is called as pole pitch, and therefore we see that if it's actually the physical distance between the poles, and if d is the diameter, now this distance is measured along the air gap, distance between the centers of two adjacent poles measured along the air gap. If we have a look at this, the air gap diameter is same as the diameter of the rotor core, or since the air gap is small, it is sometimes taken as the inner diameter of the stator bore as well. Therefore, if let's take it in terms of the rotor, so if d is the diameter of the rotor, the pole pitch, which is usually denoted by tau, it will be equal to pi d by p. Pi d is the circumference divided by the total number of poles. If there are only 2 poles, then it will be pi d by 2. If there are 4 poles, pi d by 4, and so on and so forth. Sometimes the pole pitch is also measured in terms of number of slots over the periphery of the armature. Now another definition which we will like to revise, you must have studied this in your earlier course as well, is the coil span, or also known as coil pitch. Coil pitch or coil span, as the name therefore suggests, it is the distance between the sides of a coil. We have in each coil we have two coil sides. For example, in it when we had considered one slot pair, this was the distance between the coil sides, and when we considered two coils, we had this as the distance, right? So the coil span is the distance between the two sides of a coil. Now, as far as this distance is concerned, it's not usually measured in terms of the physical distance as in the case of a pole pitch. It is measured in terms of either the number of slots spanned, in terms of number of slots spanned by two coil sides. Here we have not shown any slots between these, but in an actual armature there are so many slots on the armature surface, and therefore if we measure the number of slots spanned by the two coil sides of a coil, we call that as coil span. Another way of expressing the coil span is in terms of electrical angle, also measured in terms of the electrical angle between two coil sides. Now, if we have a look at the pole pitch, it's the distance between centers of two adjacent poles, and the two adjacent poles have opposite polarity. That means it is the distance from the center of a north pole to the center of a south pole, and we see therefore electrically the angle between the center of a north pole to the center of a south pole, it is equal to 180 degrees, because from the center of a north pole to the center of a south pole and back to the center of the north pole, there is one full cycle of variation, which is equal to 360 degrees electrical. And therefore from the center of a north pole to the adjacent center to the center of the adjacent south pole, the electrical angle will be 180 degrees. Therefore the pole pitch is always equal to 180 degrees electrical. Now, if the coil span, which can also be measured in terms of the electrical angle, is also equal to 180 degrees electrical, that is, the coil span is equal to the pole pitch. Such a coil is known as a full pitched coil. Full pitched coil. And the whole set of coils which are connected together to form a winding is known as full pitched winding. We have this term associated with the whole winding. And sometimes deliberately the coil span is kept lesser than 180 degrees electrical. Coil span is less than 180 degrees electrical, or in other words we can say that if the coil span is less than the pole pitch, the coil is known as a short pitched coil. Also known as a corded coil. CHORDED, corded coil. So we have a short pitched coil or a corded coil, and the winding which is formed by short pitched coils is therefore known as a short pitched winding. So for now we'll close here. Thank you and take care.